Hey y'all, CJ Burke here with DevelopEV, and today we got a special guest, Justin, and we're going to talk about everything switchgear. If you've developed EV charging infrastructure in the industry for a while now, you probably already know that switchgear is one of the most challenging parts of the EV charging process because it's so difficult to get. There's so many problems. I'm sitting here banging my head against the wall of like, why is this so hard to get? Why is the lead time so long? And Justin here is going to give us all the answers. So, Justin, you want to do a quick intro?
Yeah, thanks for having me on, CJ. This is great. I'm Justin Haesemeier. I'm a senior field sales engineer for Milbank Manufacturing, and we are manufacturing headquartered in Kansas City, Missouri. And our plant, we get rolls of steel and aluminum in, and we take it all the way from that to the cabinet, and then to the switchgear, the industrial control panel is what we make. Which is then shows up at the EV charging site to power the chargers. So,
Awesome. And Justin and I have been in the trenches. We've worked together before, working late Sunday nights, trying to get drawings out and stuff. So we have a lot of experience together on this jointly shared misery and also jointly shared successes. So first question is, what is switchgear? And I know even the name switchgear is technically not always right in the code book on like what is switchgear, what is AC panel board, and all that kind of stuff. So let's just explain to the viewers of like what is switchgear.
Yeah, absolutely. So switchgear, it's kind of like catch-all really for the EV charging sites. You can also see switchboards or industrial control panels, but they all really serve the same purpose. And that is at the EV charging site, you have the power coming from the utility company, and then it goes to the switchgear, which would have like a lot of times the metering and the circuit breakers and everything. And then that feeds the power cabinet for the EV charging site. So it's a essential part in the middle of the chain from going from power from the utility company to the EV charger. So.
Awesome. And I know it's one of those things where it's like that ugly gray box. It's not the transformer. That's something that's owned by the utility, but this is actually a customer-owned piece of equipment. So you as the developer are actually responsible for procuring this for your project. It's not something that the utility necessarily does. And if you've never built a project before, if you've never been in this industry, like probably don't even know what this thing is. And now after this video, hopefully you're going to walk around and see them kind of all out and about, like near, street lights, next to your gas station, next to, in the backside of a Walmart. But they are very common. Every, electrical use in the country has some sort of gear behind it that is kind of the interface between the electric utility and essentially your load.
Yeah, you'll see it at every single EV charging site. Yeah, big gray boxes, or sometimes they're white too. So it's usually one of those two colors. And yeah, sometimes they'll block it off out of view for the charger site, but a lot of times you can go any EV charger site and it's right there, probably about like 7 feet tall piece of equipment. So
yeah, they're definitely not small.
Yeah.
So we're going to talk a little bit about the major components because that actually comes into play when it comes to lead times and all that, because different components of the switchgear have different lead times. That can be kind of the long pole of the tent of what it takes to actually get the switchgear delivered onto your site and actually installed.
Yeah. I'll start off. The first major component is like really where you terminate the wires, the line termination section. And then typically it'll go to the metering section. So this is where the power company, they need the meter to monitor the power and know how much to charge for everything. And so then that's typically the next step. You'll have like the current transformers oftentimes will be there, although sometimes those will be upstream too. And also the meter. And then the other critical part too is of course, the circuit breakers. A lot of times you'll have power circuit breakers, or you can have molded case circuit breakers. But I mean, these EV charging sites can be up in the thousands of amps. So these are really large, powerful breakers in there. And then after that, you can also have control equipment too. That can be site specific. But I would say those in general, kind of the generals, what's in switchgear. So.
Yep. And when it comes to the metering section, I think that's the part that changes the most between different utility service territories, because every utility has different metering requirements. And that's actually one of the things that you guys work on a lot on the day-to-day, is that your parts list is, hundreds of thousands of pages, right? Because every utility just does it differently, unfortunately, right?
Oh yes, yeah, yep. And there's what, thousands of utilities throughout the country, and so you can kind of West Coast ones like it's similar, and then also like Northeast ones as well. But in general, they still have their own specs. They have their own requirements for their safety and for how they're doing the metering. So each one has their own little variety for it. So yes, you're right. So it does add up on SKUs for us.
Yeah, and you talked a little about the current transformers, the CTs, as you'll kind of commonly hear them referred to. Why is it sometimes that they're in the transformer? Why is it sometimes they're in the switchgear itself? So, like sometimes they're in like a separate like CT cabinet. Like, what generally determines where they go, and what are some good kind of rules of thumb to kind of go by?
Yeah, so a lot of times it can be up to utility, but I think probably maybe the most convenient spot is in the utility transformer, which is just upstream of the switchgear. But the issue you can run in with that is if that utility transformer is feeding more power sources than just the EV charging site, then they need to meter each one of those separately. And so oftentimes they'll then have it in the switchgear. And so then usually you'll have the service disconnect, which is like the spot where the utility is like, okay, our responsibility ends here. Now you cover this equipment from this on. It's your customer owned equipment. And so they'll also that's why they'll oftentimes put it in the switchgear. But then other utilities, like they prefer having a separate CT cabinet that just has the CTs. And they're like, this is the CT cabinet we use. We'll mount it here. And that's what you need to install this in our territory. So that's up to their choice as well. So
Got it. And I think the general preference in the EV charging industry, at least my personal preference, is having the CTs and the metering like on the transformer, because then us as the developer, like we don't have to worry about a lot of that stuff. It's just kind of all in the utility. They kind of maintain it. And frankly, if it's essentially the cash register for the utility, I kind of like how they kind of take that on inside of their own equipment, because like I don't want to have to worry about that as much. And if your gear's unmetered, right, and this is something that you and I worked on a lot, is that if the gear's unmetered, you can order that a lot quickly and a lot more consistently, because there's not all those differences between utility metering section requirements, spacing, different jaws on the meter and all that. The utilities is taking that on themselves, right?
yeah, it's a bit of an easy button when they can do it like that, because then those transformers are designed where they can have the CTs right there too. So it's already set up for that. And then otherwise, if it's not in there, you got to really comb through like our single lines and wiring diagrams and making sure that the height of the meter is right, and then the height that they're landing their wires for the termination of the CTs is also correct. And so, there's a lot more steps you got to follow. Whereas if it is right there in the transformer, then it's, like you said, it's all set up and done already. So, and it meets their specs. So
Exactly.
it takes up a lot of space too. So it is a space saver if they have them in there. So
yes. And I think one quick thing on the circuit breakers, right? There's two. I like to think there's kind of like two general kinds that we'll use, right? There's like, your thermomagnetic breakers for the branch circuit breakers, and then there's ones called like ETUs, electronic trip units. Do you just want to briefly go over like the difference of those and some of the pros and cons?
Yeah, absolutely. So the thermomagnetic ones, those are really kind of more the traditional ones, and they're, just to put it simply, like they work by heat. So the more current flowing through them, the more they have something called a bimetal. It heats up, and so if it heats up too much, then it's going to move down, and then it's going to cause the breaker to trip. So it's like actual physical, like the latch swings. And so those are, if it's, let's say you have a 2000 amp breaker and you have 2500 amps running through it, then probably after like 10 or 15 minutes or so, it'll trip. Whereas the ETU, the electronic trip unit you were talking about, you're really seeing those more and more. But those are, they're worked electronic. So They just have their own little CTs in there, and they are actually measuring the current versus like tripping by heat. And so if it measures the current and then it has its set trip curve, which is basically it's programmed for trip in these situations. And if that ever happens, then that's when it causes the breaker to trip and open. So, and the electronic trip breakers are, I think, you're probably becoming pretty common, because then you can also adjust tons of settings. You can long trip, short trip, instantaneous trip. So I think we're seeing more and more of those for EV charging, especially level 3s. So.
Yep, especially on those DC fast chargers, because with those ETUs, you can actually better coordinate your protection settings as well, kind of all the way upstream, where with thermomagnetic, you're kind of stuck at that rating. But with ETUs, you have the frame rating, which is like kind of the max that it can trip to. So on a drawing set, you'll see like 400 amp frame, 300 amp trip. And there's certain like kind of step intervals that you could kind of turn the dials to that they can trip on. So if you're putting in a different charger later on that's under that frame rating, if you need to make an adjustments from a safety standpoint, you kind of have that with thermomagnetic, you're kind of stuck unless you are going to completely rip and replace and put a different breaker altogether in there, right?
Yeah, you can control, like a lot of times you don't want the main breaker to trip if there's an issue with like just one charger, because then who knows, the main breaker trips, it's feeding everything. And so if it goes, then everything, all the power goes. And so, yeah, so like you said, you can adjust the settings for the selective coordination. And so I want this breaker feeding this charger to trip if it has a short there or something. I've also heard too that sometimes the breakers will nuisance trip from inrush current when the charger turns on. And so you can also like adjust the short trip. And so then that way the breaker program, it allows, okay, we'll allow this much extra current flowing through when it starts out. We won't trip. Like, that's okay. And so then that way you can also reduce nuisance tripping too. So,
yeah. I always kind of think of it, it's like an iPhone, or it's like, like a rotary phone. You just have so much more capability within those programmable breakers. And obviously there's a cost impact on that, but I think it just gives an EV developer more flexibility and not kind of being stuck in a corner with those thermomagnetic breakers, especially on the branch circuit breakers. So next we're going to talk about a topic that is kind of near and dear to my heart, because it's caused me a lot of strain, but is bracing. So, you'll see different ratings like 65K AIC, 150. Like, what does this mean? And like, why is it important when we're developing these EV infrastructure projects?
Yeah. So the 65KA, 100KA, that short circuit current rating or the fault current rating, that is, let's say there's a short circuit like between phase to phase. So now there's no longer the loop is like completed between phase to phase, which means the load is only the wire in the copper. So then the resistance goes like way low. And so with Ohm's law, when the resistance drops way down, that means the current goes way up because the voltage stays the same. And so when you have this short circuit or a fault current, then the amperage just shoots up. So let's say you have a 2000 amp site and you have a short between phase to phase, then the fault current, you can actually measure it based off of the resistance in the copper wire. And so they'll calculate that. And whatever it is, you need to design your equipment to be able to handle that short circuit above that. Because if you don't, then a lot of times when that happens, there's a significant amount of energy with this, thousands of amps. And so then it can cause explosions. And it can also cause people to cause injuries, like kill people. So it's like, so that's why it's very important to measure your fault current and to make sure that you have equipment that meets that.
Yep. And it's not just the main breaker, right? Like, you can't just have like a main breaker that's sized to 65, right? It's like the whole gear itself, right? Like the enclosure, the main bus, everything downstream. Is that right?
Right. Yeah. Yep. So like you said, the bracing, making sure that the busing can handle whatever amount of energy it is. So that way, if that happens, then it couldn't cause like the bus to like come apart and go flying. and then wires in it as well. Like wires are like whiplash. Like they can even like we have a lab at our building, and we'll actually, if you'll see the wires, they'll actually like whiplash and hit the front cover, and they can actually knock it off sometimes. And so like that's the amount of power going through it. So yeah, so that's why it's not just like the breaker. Although you design the breaker to trip as quickly as it can to reduce the amount of energy that goes into it, but then you also have equipment design to be able to withstand whatever fault current will be running through. So yeah.
Yep. And if you can just YouTube search like arc flash explosion, and you can just watch that, and you'll understand why this is important from a safety standpoint, because it's something that you never even want to see because it's so bright, or even be in front of it because it can cause a lot of burns and stuff. When it comes to bracing and like, the fault current, like where does that information come from? Obviously an engineer has to design that, but like what's like the input information from the utility that you need to make those calculations?
Okay. I know it's like distance to the transformer is a key part, because then the shorter the distance, the shorter amount of copper wire. And so then that lowers the resistance, which then increase the amperage. So if you're actually further away from the transformer, the fault current will be lower just because you have more internal resistance of the wire. So I know that's a critical part. And then also just the voltage and the amperage already there. So I'd say those are the main compartments for calculating it.
Yep. And when you are developing these EV infrastructure projects, it is always so critical to coordinate with your utility contact to get that fault current information, or calculate off of what's called infinite bus. So you just calculate the worst case scenario that could ever come out of that utility transformer, regardless of how long those secondary conductors are running from the transformer to the switchgear. Because that's like worst case, if the utility is very slow or they're just not getting you what you need, you could always do that. And you might pay a little bit more on the gear and overbrace things, but at least you're able to move forward and get your project built.
Yep. Yeah, and I know the higher you rate it too, then a lot of times the more expensive the equipment has to become, because then all the breakers you got to get have to be designed for that, or sometimes if it's high enough you got to get like fusing, because fuses can trip very quickly. And so yeah, but depending on the fault current level you pick, it could also impact the equipment and the cost as well. So it's kind of like knowing what you need, but then not trying to over design so you don't drive up the costs and stuff. So yeah.
Absolutely. So next we're going to talk about some of the procurement challenges, and this is kind of like the crux of a lot of this is like, why am I always banging my head against the wall? Like why is it like this huge lead time, or why am I waiting for this one little part? I feel like I could just go fly to Germany, pick it up and fly it back, and that would save me time. But what are some of the challenges that you guys are running into as like a gear manufacturer, and like how are you guys like overcoming those, and kind of the industry as a whole?
Yeah, this is a topic I've been pretty involved with actually over the last like couple of years, because I mean, when we make our equipment, like we are sourcing materials and product from a bunch of other vendors as well, and so we are kind of at their mercy at how they're doing with supply chain. So even if we have like capacity open at our plant, if like we're missing like one part, like if we're missing like a lug or a breaker, like we've had to delay stuff for both of those. Then it's like we can't finish the product and get it shipped out to the site. So I know that was something like last year, we have to be ordering like months ahead of time. And so we had some orders delayed, but now that's something we've been working on. We're actually working on procuring parts like 6 to 12 months ahead of time now, just to make sure we have them. And so that way we don't have any delays with our orders. But I mean, we'll buy it from a vendor, but a lot of times they'll buy something from a vendor as well. So we'll be like, hey, we need this breaker or something. And they'll be like, well, we're waiting on this plastic part that's coming from Europe somewhere or something. And so then it's kind of like multiple steps in the chain. So if any one of them gets held up, like it could delay it by months even. So
absolutely.
Yep.
And like, where are a lot of these kind of key parts made? I know there's a lot of stuff with like, the IRA and all these like federal programs are trying to like onshore a lot of stuff, but I always feel it's focused on like the sexy stuff in the industry, right? Like the chargers and all that, but they kind of forget a lot about like I call it like balance of plant, like the switchgear and all that stuff, where I think a lot of that's, or like the components of that are still overseas, like the main breakers. Is that correct? Or are you seeing a lot of that stuff come more to shore?
A lot of times they are assembled in the US.
Hmm.
So like the breakers, maybe they'll like buy the parts from other parts like Europe or Mexico or Asia. And then like they'll have a plant in the US where they'll assemble them. So you'll see that, but then otherwise, yeah, you'll still see parts really all over. So we'll buy parts still we buy some from Canada, we buy them in the US, Mexico, Europe, Asia as well. So yeah, for supply chain, I know we're still seeing it like just all over the place, really. So I would say probably the most common for the final, like for buying a breaker or some other finished part that it will be final assembly, typically in the US, I would say. So.
Oh yeah. Yeah, just because it's such a heavy piece of equipment. It's like logistically, it's hard to assemble, in
Yeah.
like Taiwan, right? And just like shipping it over in like a container ship, because I mean these things are huge, bulky, heavy. It just logistically it's a challenge. So it's just easier to assemble it here. But hopefully more. At least my hope is most of these parts get more onshore in North America, so that there's less challenges with international shipping or international conflict. Which is becoming more of a thing here in the 21st century, unfortunately. And lastly, we'll talk about a big thing is utility approval. So we talked a little bit about this earlier in the episode, but a big component of this is that this is the handshake point between you and the utility, and you're kind of taking control of the power and all of the responsibility from the meter moving forward, or from a certain disconnect point moving forward. So why do we care what the utility says, right? I mean, this is our own piece of equipment. Like, why do we need to comply with their requirements?
Yeah, I mean, it's their territory, it's their power, right? And then they have to have their people working on the equipment, and so they're at the forefront of their mind is safety for their people, their personnel. Yeah, and then they also have their own standards for how they do the metering, and the way that they just monitor the power. So basically, I mean, you're using their power, and so they're the ones that control the switch, and so they say this is the way we do it, and that's how you have to do it. So, but yeah, I would say safety a lot of times is the top reasons why they'll do stuff. They're working on equipment for how they want it set. They want to make sure no issues, like it's easy for them as well to handle. So, and then I mean, with the utilities, like you kind of have some standardization where, like, of course, you got like West Coast. I don't know if with the USERC. So generally, they all follow similar standards, but then it is kind of a little more scattered east of the Rockies, where it's kind of utility can vary quite a bit in terms of like the meter sockets they use. I don't know, the number of terminals in the meter socket, what kind of CTs they use, and then like all the dimensions that they have required for like landing heights, and so yeah. So then for the utility, so basically, since it's their power, it's like they tell you like this is how you're going to use it, and so that's how you do it. So,
yep. And you used an acronym there, USERC, and I know that comes up a lot, especially west of the Rockies, where I'm located in Arizona. What is that, and like, do you see that helping EV developers and I guess people in general that are building out the gear, or do you see it complicating things more?
I personally think it helps, just because then we have this one design, and then also like we can look up, all right, here's the requirements. If we have like 2000 amp cabinet, then we can go look up, they have USERC drawings. We can go look up, all right, here's the dimensions they're going to hold us to. Here's what we got to make sure we meet for the materials. And if we follow that, then pretty much everything west of the Rockies, like we would be approved. There's still some variations. They're kind of like you can kind of call them maybe like guidelines over rules somewhat, but in general, that is what they'll say, like, hey, you need to follow this USERC drawing 329B or something like that.
Yep.
And they'll have it mapped out too. So for us, it is an easy reference for knowing what is needed in our equipment. So I think I think it helps with it because then it's a little more piecemeal. It's kind of more like we have to work one-on-one directly with the utility to get approvals otherwise.
Hmm.
And so, whereas with USERC, we can kind of just follow that design standard for them. And then pretty much from like Washington all the way down to Arizona, like we can be pretty well covered. So,
Yep. And I have found on the developer side, so like when we're going out and getting the written utility approval of our switchgear drawings, which is always a good double check that I recommend to all developers in the EV industry. If you are building these projects, always get written approval from the utility that the design meets their standards. Sometimes there's portals you submit them to. Sometimes it's just the utility rep saying, "Yep, that works," in an email. But save that as a PDF and never lose it, because
yeah.
sometimes they go back on what they say. Um, so it's really cool that at least in USERC that it does help a little bit with that. And I think they are pretty clean too, because everything's kind of included in one. It's not always the easiest sometimes, because I do prefer to have the metering and CTs in the transformer, but it is a very clean build aesthetically, if there is a way to describe this ugly gray box or white box that's out there.
Yeah, you're right. They do require having the CTs and stuff with the equipment. So that is something they don't do, the CTs and with the transformer.
Yep.
So, but yeah, but then for I know like you're saying with that, getting that email or like proof of like the approval really helps because then like a lot of times you work with their standards
Hmm.
department, but then they'll have other people who are like the on-site manager, and so you kind of have to you get approved it with one of them, but then you also have to like pass it on to them and make sure, hey, like we got the blessing on this already, like we're good to go to use it. So
Yep. It's
yeah,
like, who's the ultimate boss I need to talk to get this thing
yeah.
approved? So when you're kind of going out and building or like building your designs and all that, where are you getting a lot of this information of like what what the requirements are for switchgear within a specific utility service territory? Is that all like in the ESRs, the electric service requirements, or are there separate documents that you also look at?
For utilities, normally we'll use like the ESRs, electric service requirements. I mean, the user drawings will follow that,
Hmm.
and then we'll kind of follow the other larger utilities through east of the Rockies. We'll just kind of check their standards as well. And then, I mean, for the actual design, then we also have the UL standards that we follow. So you got UL 508A industrial control panels, UL 891 switchboards. So those all have requirements for what our designs have to have. So if you have busing, like how big does the copper have to be to carry this amperage, and like how do you have to bolt down this busing, and what thickness of material does the enclosure need to be? So all that stuff is in UL too. So.
Okay. And when it comes to sizing of gear, right, a lot of that's determined also by the ESRs, the electric service requirements, of like what the largest secondary size that the utilities will allow it. And I think it, generally speaking, will go from like 4,000 amp at the highest, usually maybe sometimes 5,000 if you're lucky, all the way down in stepwise, right? What are some challenges when you're kind of talking about these larger switchgear sizes and main breaker sizes when you're kind of getting into those categories? Do a lot of these challenges with utility approval and procurement get worse, or is it about the same in your experience?
I actually think it gets a little more consistent with higher
Okay.
amperages. So it actually gets a little more simple. It's more because then it's kind of like here's, I don't know, the CT section, and then you mount the meter socket and the test switch on the side a lot of times. And then that one, the meter socket and test switch can be completely utility specific. But then actually at the higher amperages, I think it gets more consistent. Lower amperages, like you'll sometimes, if it's like just like a small level 2 site, you'll have what's called self-contained meters, and like that has a huge variety throughout
Hmm.
the country. The lever bypass, number of terminals, like there's all kinds of variables. But with CT meterings, I think it gets more consistent. So I think that does actually help for design with that. And then you just got to make sure you'll have the CTs. I mean, and then you got they'll step down the current, and then the meter socket and test switch. You just got to make sure that matches what the utility uses, because each utility has their own meter socket test switch requirements too. So,
Yep. And there's one thing that we've begun to hear in this industry, something called cold sequence. I know this is something that drives me a little bit nuts sometimes. I feel like utilities sometimes are like piloting this. They're like, we kind of want you to do this, but I'm like, okay, well, is that a requirement or is that something that you're just going to be a pain about? So like, what is cold sequencing and kind of what are some of the benefits of that? I think it's a lot from a safety perspective, but kind of curious on what you think.
Yeah, I mean, we've typically seen it with Northeast utilities. They seem to like that. And the cold sequence, it means upstream of their CTs in their meter, you have a switch. It can be a breaker, or it can vary from utility to utility. Sometimes they want like a fuse disconnect switch or something. But basically a way that they can like shut off the power to their equipment. So then they can go work on the CTs or the meter socket and not have them be live. So they don't have to be working in front of 480 volt equipment right there. And then it's also a way for them to just shut off power to the whole unit. So it's also kind of like their own main switch too. So yeah, it's something we've been running into more and more as well. So
absolutely. And from a utility standpoint too, it's if there wasn't a cold sequence switch, the only way that they could truly de-energize that meter is if they actually go up to like an overhead transformer, disconnect from the transformer, or if it's underground, they'll actually have to open up and then disconnect from either pull the bayonet fuse and disconnect potentially everyone that's connected to that transformer if it's serving multiple services. So it does provide some actual use for a utility to make things a little bit simpler. But as the EV developer, those additional requirements are challenging sometimes when they kind of come up. So it's always recommended you work with the utility, work with a good gear supplier, and understanding those requirements before you get too far down your project and have those sometimes surprises and change orders come up, because that's something that none of us want.
Yeah, 100%. Yeah, that's always it's always not fun putting out fires at the last second or be like, oh no, we're gonna be delayed months now. So I agree. Front end is definitely the best way with it, and then also, I mean, the cold sequence has a huge impact on the cabinet. So I mean, if you want a 2000 amp switch, like that takes up a lot of space, So basically, it's a new design than what it would be without it. So that's why it's important that if you catch it like at the end, and it's like, oh hey, we need to add this 2000 amp switch into this. Then be like, okay, well, we'll have to requote, and then new lead time and everything. So yeah,
I think you and I have worked on a project or two where that's come up, and it's been the total problem. So I think we both feel that almost spiritually at this point.
Yep. Yeah, I remember you were on a call last year. Yep, with it. So it's kind of like, wait, what's the purpose of this? Like, where do we need it? Yep.
So I think that's all we got for today. I know we're kind of running up against the end of time. So Justin, I just want to say thank you for joining. It's been an awesome discussion here, getting into all the nitty-gritty details about switchgear and what we all need to know when we're developing these EV charging projects to hopefully make our labs a bit easier. So, if you like this content, please like and subscribe this page. We'll be coming out with a lot more content like this and bringing in other experts like Justin to talk about these really important subjects. If you like this video, also comments. I know there's gonna be a lot of good questions from the viewers on all the cool stuff that you guys are experiencing that we can also answer for you. So Justin, thanks again, and look forward to having you on future shows and discussing this industry, and also buying gear from you too, because we also do business together. So thanks again for coming on.
Yeah, and thank you, CJ. That was great, and appreciate it. Enjoyed coming on too. So thank you.
Awesome. Thanks, guys.